Assalamualaikum and hello to everyone. For today's lesson, we will cover part 2 for chapter 2. You can pause the video to read some of the disclaimers regarding this video. On the left of the screen, written in red is the subtopic for today's lesson, and on the right of the screen, also written in red, is the objective for today's subtopic. Now, before we begin our lesson, let's review on what we have learned about closed system and its first law energy equation from chapter 1. You can pause the video to have a quick read regarding this. Here are some key points or concepts that students should be aware of when we go through this subtopic. For the first process, the common name is constant volume. The thermodynamic name is called isochoric, and the third type, and this is only for gases, is in the form of PV by the power of n equals to C, where n here is the index number, and n can be either infinity or negative infinity. The line for this process is a straight vertical line. Now, remember that for a process to occur, there has to be a minimum of two states. The figure given shows the process line for a compression process at constant volume. The process line can also move in the opposite direction. Next is the boundary equation for this process. In chapter 1, we learned that the boundary work is simply the area under the PV graph. And based on the process line that we have seen just now, there is no area under the graph. And that is why the boundary work equation for this process is equal to 0. Next, for the first law energy equation, start with writing the general equation. And since the boundary work is equals to 0, the first law energy equation is reduced to the following. Delta U here has to be expanded into its specific internal energy form, and from here, students should know how to determine the values for specific internal energy based on the substance. Now, let's look at the first example. You can pause the video to read and understand the question properly. For the first step, please try to draw and label the schematic diagram. Since the question involves a process, there has to be two states, state 1 and state 2, connected by the isochoric heating process. For step 2, try to write the required equations. To solve for volume at state 1, we can use the ideal gas equation PV equals to mRT, and to solve for the amount of heat transfer, we will apply the first law energy equation for this process. Remember that the substance is a gas, therefore U has to be replaced with its specific relationship CVT. For step 3, determine the required properties to fill in the equations. At state 1, we can straight away solve for the volume using the ideal gas law. At state 2, we have to find the temperature. This can be solved by either using the ideal gas law or the combined gas law. Now, for practice purposes, let's try to use the combined gas law to determine the temperature. Since volume is constant, we can reduce or simplify the equation, and by substituting the required values, we can solve for T2. For the fourth step, substitute and solve for the amount of heat transfer. Now, let's go through the second example. You can pause the video to read and understand the question properly. For step 1, again, please try to draw and label the schematic diagram for this question. Since there is a process involved, there has to be two states, state 1 and state 2, connected by the heating process at constant volume. For step 2, write the required equation to solve the amount for heat transfer. This can be done by applying the first law energy equation for this process. Now always remember to expand the delta U equation into its specific internal energy form. For step 3, determine the required properties at each state. At state 1, since we know the phase is a mixture, we can solve for the specific internal energy at state 1 using the equation of mixture. And also using the equation of mixture, we can solve for specific volume. Now this is because we have to calculate the mass of the substance. At state 2, after determining the phase, which we can see here is still a mixture, we have to calculate the new quality at this state. We can then solve for specific internal energy by using the equation of mixture. For step 4, substitute and solve for the amount of heat transfer. Please take note that due to decimal points taken during calculation, there might be a slight difference between the given answer. For the second process, the common name is constant pressure process. The thermodynamic name is isobaric, and in the form of PV by the power of n equals to C, n here equals to 0. The process line is a straight horizontal line, and the figure given shows an example for an expansion process at constant pressure. The boundary work equation for this process is given by the product of pressure, which is here constant, multiplied with the change in volume. For the first law energy equation, remember to start with the general equation. We can then rearrange the equation to find for Q or heat transfer. Now, the equation delta U plus W here can also be replaced with delta H. This is because since delta H is also equals to delta U plus PV. However, I don't recommend using this form of equation as it may be quite confusing. And the same as before, delta U can be expanded into the following form. And from here, students should know how to find the values for specific internal energy based on the substance. Now, let's look at the first example. You can pause the video to read and understand the question properly. For step 1, please try to draw and label the schematic diagram. For this question, it involves an expansion process, therefore there has to be two states, state 1 and state 2, connected by the expansion process at constant pressure. For step 2, to solve for the first item, we will use the boundary work equation. And to solve for the second item, we will apply the first law energy equation for a constant pressure process. For step 2, at state 1, since the phase of the substance is given, which we can see here is a mixture, to calculate for the volume, we first have to calculate using the equation for mixture the specific volume. After that, we can solve for the volume at state 1, which we see here equals to 1.7402 meter cube. We can also calculate the specific internal energy using the equation for mixture, which we can see here equals to 2290.49 kilojoules per kg. At state 2, since the phase is not known, we have to first identify the phase. This can be done by opening the table A5 since the substance is water, and at pressure 700 kilopascal compare the temperature temperature with the saturation temperature, and since the temperature is higher, therefore the substance is in the superheated form. So for superheated vapors, we have to refer to table A6 for pressure 0.7 megapascal. Unfortunately, there is no table for 0.7 megapascal, only for 0.6 and 0.8 megapascal. Now this requires us to use the interpolation technique to determine the required properties at 0.7 megapascal. For those who do not remember the technique interpolation, please refer back to the previous example in subtopic 2.2. By doing the interpolation, we can get the values for specific volume and use it to calculate for volume, and also we can interpolate for the value for specific internal energy. For step 4, substitute and solve for the question. Now let's go through the second example. You can pause the video to read and understand the question properly. Please try to draw the schematic diagram for the question. For this question, it involves a compression process at constant pressure. For step 2, using the gas equations, we can solve for the temperature at state 1 and state 2. For amount of work required, we will use the boundary work equation for constant pressure process. And for heat energy involved, we will apply the first law energy equation for this process. Since the substance is a gas, remember to replace U with its specific heat relation CVT. For step 3, at state 1, using the ideal gas equation, we can solve for the temperature at state 1. At state 2, using the combined gas law equation, we can solve for temperature at state 2. Now we can solve, or maybe we can sketch for the PV diagram, okay, as given in the video. And for the fourth step, substitute and solve for the required question. Negative work here means that work is being put into the system, and negative Q here means heat is leaving or is being removed from the system. We have come to the end of today's lesson. For questions, please do not hesitate to leave a comment in the related forum section. Please refer back to the original notes for exercises. Thank you for your attention and have a good day.